factoids about Lars that I found on the internet today, but he really keeps a very low profile. Like, his Wikipedia page has like 3 lines on it. So it's real. He doesn't even have a CD on the internet, as far as I could tell, which is because he doesn't need one, because he's so famous. So Lars, the two things I can find, which I can tell you, is that Lars is part of the National Academy of Sciences, which is like very prestigious. For those of us that live in America, we understand that. He also has 64,000 citations, which is so many citations. And he has a lot of really the most foundational results in our understanding of galaxy formation and evolution. He showed that the Lyman alpha forest is due to essentially absorption in the IGM of diffuse gas, i.e. the cosmic web in filamentary structures. He showed how galaxy collisions drive gas to the centers of galaxies, inducing starbursts and forming the centers of massive elliptical galaxies, i.e. our understanding of how mergers drive the growth of galaxies. He's going to kill me, he's so embarrassed. And he also described how energy injection from quasars regulates star formation in galaxies. He has a galaxy profile bearing his name, the Hernquist profile, which we've all heard of. And he's really foundational for a lot of the simulation methods that underlie most of the giant cosmological simulations that are known today. In particular, both the algorithms and the subgrid models that are used in these simulations. And he's responsible for building Illustris, the biggest, baddest simulation ever, I can say, because we're at Harvard. But really, he is the father of cosmological simulations of galaxy formation. So we're delighted to have him here today. Thanks, Lars.
Thanks, Erica. So the first question I want to answer is, this is a real stamp that's produced in Germany. So if you go to a post office in Germany, you can actually buy this thing. And I wanted to show just to prove that there are governments in the world that still care about science, even if ours doesn't. Okay, so I wanted just to give a sort of overview of some of the work I've been involved with. And the goal of this is to produce a fully predicted theory of galaxy formation and evolution. And the fact is that we don't have such a thing yet, but there are many good reasons why we would like to have such a theory. So I think this is a field where the observations and data have been far ahead of the theory for quite a long time. And for the health of the field, it would be good if the theory actually caught up at some point, because we'd like to have a theory to be able to interpret, say, surveys of galaxies and observations of individual systems, how individual galaxies appear the way that they do, and how that fits into the overall cosmic structure that we see in the universe. And we'd like to be able to relate luminous galaxies to the underlying dark matter, which forms the backbone of the large-scale structure that we see in the universe in the form of the cosmic web. And finally, we'd like to understand physically things like the origin of stars, galaxies, quasars, and supermassive black holes. And it turns out that all of these play an important role in galaxy formation and evolution. And we'd like to test the basic underlying theory that we have, or paradigm of structure formation, by predicting where the galaxies are and what their properties would be, so we can relate, like I said, the luminous material to the underlying dark matter. Now, this is a problem that's been around for a very long time, and it's a little bit unclear to me exactly when we should think about it started, possibly as early as the 1920s and 30s, when galaxies were recognized as separate entities and the expansion of the universe was discovered. But a foundational, well, then furthermore, the discovery of quasars and the cosmic microwave background in the 1960s really gave us an idea about the vast scale of the universe. And I think the first quantitative attempt to model galaxy formation theoretically was this paper in 1962 by Egan, Lin, Bell, and Sandage. And what they proposed was that galaxies are formed by monolithic collapse of giant clouds of gas from the intergalactic medium. Unfortunately, things are much more complicated than that, which is why we don't have a solution to this problem yet. And if things had actually been like they envisioned, galaxy formation probably would have been solved decades ago. But subsequently, it was realized that dark matter is very important and dominates the matter density of the universe, And furthermore, we know that our universe is hierarchical. And so this idea of monolithic collapse just doesn't really make any sense. In a hierarchical universe, the important ingredients that provide sites of galaxy formation are dark matter halos, and they're subject to mergers that have to be accounted for. And I think the greatest complication of all, as I'll describe shortly, is starting around the 1990s or so, the critical importance of feedback processes was realized that regulate star formation in galaxies. And we think this comes both from stars through stellar evolution, as well as supermassive black holes. And that introduces enormous complications in trying to formulate a well-defined theory. Now, there is some good news in all of this, that we have a well-defined starting point, and that's provided to us by observations of the cosmic microwave background in type 1a supernovae. And in particular, they tell us what the underlying cosmological model of the universe is, and furthermore, what the universe is made out of. And so together, these things provide us with well-defined initial conditions that we can use to evolve forward in time and see what sorts of objects are produced through the action of various physical processes. Furthermore, on large scales, we believe that the dark matter is affected only by gravity, and so the evolution of that is well understood. And so, for example, in the background here is an image from the Millennium simulation that was done in 2005. That was a large n-body simulation of dark matter in the universe. And you can see, due to the nature of the initial conditions, that the dark matter collapses into this filamentary structure known as the cosmic web. And at the intersections of the filaments are dark matter halos that would provide sites of galaxy formation. However, we want to relate the underlying dark matter to what we actually see in the form of luminous material, then we need to account for the physics that affects baryons. And that turns out to be much more complicated. In particular, the evolution of baryons is highly nonlinear. There are no obvious symmetries present. And worst of all, we're confronted with a problem where there's a huge range in various scales, both, well, all three of these, length, mass, and time scales. And so that leads to the bad news in this problem, and that is that the evolution of the luminous component is problematic. And the reason for that is sketched out in this diagram here. So the scale here is arbitrary, but the gold line is the halo mass function that we think corresponds to our real universe. And then superposed on top of that, and forget about the vertical scale, just compare the shapes. This is the galaxy stellar mass function locally. Now, if all dark matter halos contain the same fraction of baryons everywhere, and those baryons were converted into stars at the same rate independent of scale, then this black line here should lie on top of the gold one. But you can see that it doesn't. And this means that star formation is less efficient as a function of, say, halo or stellar mass of galaxies. And in particular, it's suppressed both at low masses and high masses. And we think this is due to the action of feedback. And we don't understand these processes in complete detail yet. But the best bet is that at low masses, it's regulated by feedback from stars. And on high masses, it's regulated by feedback from supermassive black holes. Unfortunately, we don't understand these things in detail. And so that means makes modeling the difference between the baryonic distribution and the dark matter one difficult. And the really bad news is if we think about what this implies for the scales that we have to model, right? So we're dealing with feedback processes that originate from very small scales inside of galaxies. So things like this, galactic winds being driven by intense star formation in the center of this galaxy, or worse, feedback being caused by the supermassive black hole in the center of this galaxy. And what this means is that very small scales within galaxies can couple not only to the ISM of galaxies, but the surrounding circumgalactic medium, as well as potentially the intergalactic medium. And so what this means is that all the scales in this problem are coupled together. So we can't just separate the problem by scale in the way that Egan and Lindenbell and Sandwich had imagined. We have to solve all the problems together simultaneously. And that just makes it very difficult. And it also means that this is essentially a computational problem in the end. And so to illustrate the problem with this dynamic range issue we have to deal with, ideally what we would want to do is simulate, the entire observable universe or some large portion of it that would be several gigaparsecs across. But at the same time, we would like to be able to model the internal structure of galaxies, which is described on scales of order, say, kiloparsecs or so. And then if we have to account for these feedback processes, ultimately we would need to account for things happening on scales of 10 to the minus 3 or 10 to the minus 4 parsecs, which is characteristic of, say, the accretion flows around supermassive black holes. And so if you think about this for a minute, if you wanted to do, say, a single simulation to capture all of this, the dynamic range and scale that you would need to go from here up to here is roughly 13 orders of magnitude. Now, with the fastest, most powerful simulation codes that we can run these days, we might be able to achieve a dynamic range per dimension of, say, 6 orders of magnitude. So per dimension, we're about 7 orders of magnitude short of being able to do this whole problem. And so if you think about what that means in 3D, if you wanted to introduce enough resolution elements to do something like this, we're short of that by 20 or 21 orders of magnitude. Now, you might think that given Moore's law, we would just have to wait a certain period of time to be able to do such a computation. And Moore's law is a factor of 10 every 5 years. So a factor of 10 to the 20 could in principle be achieved in 100 years' time. But unfortunately, there are good reasons to believe that that will never be possible. So if we just think, for example, about the power requirements, the sort of supercomputer centers I use to do these simulations consume of order 1 or 10 megawatts. So if you scale that up by a factor of 10 to the 20, you're talking about the luminosity of the sun. So obviously, this is completely impossible using existing technology. And even if you could reduce the power requirements by 10 orders of magnitude, this would still be impossible. So unless there's some drastic revolution in computing technology in the coming future, at least in the foreseeable future, carrying out a calculation like this would be impossible. And so instead what we have to do is we have to truncate these scales both at the upper and lower ends. So rather than trying to simulate the entire observable universe, we typically simulate regions or maybe, say, 100 or a few hundred megaparsecs across that would contain a volume 10 to the minus 3, 10 to the minus 5 of the whole universe. And then we have to truncate this hierarchy here also and not try and resolve directly things like accretion onto supermassive black holes. However, we still have to account for this sort of process, and so that means that these things have to be included in the modeling as some sort of sub-resolution prescription. And on top of this, we don't really understand the details of this process in a comprehensive sense, and so the models that we adopt have to be parameterized in some way, where the parameters are constrained observationally. And so getting a full solution to this from first principles is simply impossible. Instead, we have to rely on observations to guide us in the modeling and also use observations to compare the outcome to test how reliable the modeling is. Now, there have been a variety of ways to do this carry out this sort of procedure computationally, and I don't have time to review all of them today. I'm just going to focus on the work I've been involved with. But there's a nice review article by Mark Vogelsberger coming out in Nature very soon that describes all of the attempts to do this sort of attack up to now. And so this is a diagram from his paper showing some of the attempts that have been done recently, divided by simulations that include only dark matter, like the ones here on the left, and the ones that try and account for the effects of baryons in addition to the dark matter. And there are essentially two types of approaches that have been used in both cases. So one is to do a zoom-in simulation where you have a cosmological volume, but only part of the volume is highly resolved. And so you select that region to localize around, say, one particular galaxy, like, say, this one here, which includes the baryons, or, say, the Aquarius simulation that just looks at the dark matter in Milky Way type halos. The other approach is to do a large volume simulation. So like, say, the Millennium one that I just showed you, this one down here, or the ones that include hydrodynamic processes like the ones that I've been involved with, which are these two up here. So these are not the only ones. There are a lot of competing efforts that have various advantages and disadvantages. And so whether one does a zoom-in or a large volume simulation is largely a trade-off, I think, between predictive power and resolution. So simulations like this can't possibly achieve the same resolution as a zoom-in simulation is designed to. But on the other hand, I think these are more predictive in nature because they can make statistical predictions for the properties of galaxies. Whereas something like this, because the outcome depends on the models you put in, you don't really know what you should be comparing this to in reality to test the modeling. I think ultimately both sorts of approaches will be needed, because we need to come up with some strategy to combine simulations across different scales to ultimately bridge this huge range of scales we have to deal with. And so what I want to do for the rest of the talk is just to describe briefly some of the results that we have been getting from our simulations to try and convince you that in spite of their limitations, their dependence on some of these fairly arbitrary models that we have to adopt, I still think they have a fair amount of predictive power, and they can teach us interesting things about galaxies that we see and connect those to the cosmological evolution that we would like to understand. And so the first sort of attempt that we did was in 2014 with this simulation that we called Illustrious. And so Mark Vogelsberger is the one responsible for that name. I didn't choose that, and I don't particularly like it, but that's what we're stuck with. Anyhow, so if you want to look at this, it's described in this website, and the simulation data from this data set is all public now, so anybody can download it or play with it on the web. And so these simulations included both dark matter and baryonic processes, and they were done with this moving mesh code called a repo that solves the equations of hydrodynamics on a moving grid. And the physical model that we adopted is described in this 2013 paper by Mark, and I'll describe shortly some of the ingredients that went into that. And so the way that we do this is that we set up initial conditions that are consistent with observations of things like the cosmic microwave background, and we include the dark matter, the baryonic matter in the correct proportions, and evolve those forward in time to redshift 0 and compare the outcome at different times to what we see observationally. And so the sort of ingredients that go into this, like I was just saying, are that there are certain things that we have to account for that are reasonably well understood. Like, for example, gas can cool radiatively and collapse to high density. So we can account for this both in the form of primordial cooling as well as in accounting for metals due to stellar evolution, which is also incorporated into the simulations. And we account for gas recycling and chemical enrichment due to stellar evolution from stellar winds, supernovae, and so on. So those things we have relatively good models to rely on. However, there are a number of ingredients that have to be accounted for where we don't understand them completely, and furthermore, in these cosmological scales, they're unresolved. And so they have to be incorporated as sub-resolution models. And so these include things like the detailed structure of the ISM of galaxies, exactly how star formation proceeds, how feedback from supernovae and stellar evolution operates, and how that feedback couples to their surroundings. And then probably most problematic is the action of supermassive black holes that we believe is very important, especially for high-mass galaxies. And so in detail, we don't have a comprehensive model for how supermassive black holes originate, how they accrete matter from their surroundings, and how they grow in time. And worst of all, we don't have a good comprehensive model for this process of feedback where energy from the growth of supermassive black holes can be released and coupled to the surrounding media. Now, in Illustrious, we had a two-component model to describe AGN feedback, and I'm going to come back towards this at the end of the talk and describe to you some of the problematic aspects of carrying out this sort of procedure. But we measure the accretion rate onto the supermassive black holes, and depending upon the nature of that accretion, we imagine the black hole would either be visible as a bright quasar and release thermal energy into the gas around it, or in the case of this Illustrious simulation, that at low accretion rates, it would operate in something that we call the radio mode. And I'll come back and describe in more detail how this sort of method was implemented later in the talk. Now, these feedback processes, like I said, we are motivated by either observations or simple theoretical frameworks, and we put those into the simulations as sub-resolution models. However, we don't understand these processes in detail, especially these down here, and so whatever we put into the simulations is in some ways arbitrary. Now, it turned out that in Illustrious, we identified a number of discrepancies with observations, and so we were motivated to carry out a new set of simulations a couple of years ago, where we updated some of the modeling, and I'll again talk about this later, But basically what we did was to update the model for AGN feedback, as I'll describe towards the end. And this was mostly work that was done by Rainer Weinberger, who's now a postdoc here. And we also made some subtle changes to the models that we have for feedback from stellar evolution and supernovae, described in this paper by Annalisa Pilipich. There were also some new ingredients added to the simulation, so we also accounted for magnetic fields, so we solved the equations of ideal magnetohydrodynamics. We have a simple model to describe neutron-star mergers and the production of R-process elements in those events, so we can track the, say, evolution of R-process synthesized material as the universe evolves. So the simulations that we've carried out are being done in volumes of different sizes. And so the largest one is about 300 megaparsecs across. So these are not quite to scale, but just to illustrate the different volumes that we're looking at. This one here is about 100 megaparsecs across. And finally, there's a third simulation at much higher resolution, but in a more limited volume, 50 megaparsecs across. So this central one here is identical to the original illustrious simulation, but based on some of these new models for the feedback effects. This one here is a volume about 30 times larger, lower resolution, but it samples the high mass end of the mass function much better and contains clusters of galaxies above 10 to the 15 solar masses. This one here is much higher resolution, about 20 times better mass resolution than the central one, and so this one should be quite useful for studying things like Milky Way analogs. Yeah? No, that's not possible because we use periodic boundaries for these regions. So these are all generated independently, but they're based on the latest Planck results for the overall model of the universe. Okay, so these two here are run all the way to redshift 0, and the data from that is now public, and you can find that at this website here. This one is taken much longer because the spatial resolution is much higher, and so the time stepping is much finer. So that's currently at a redshift of about 0.03 and should be done in a matter of weeks. But this particular simulation will, in the end, have consumed something like 140 million CPU hours. And so that gives you an idea of the computational scale of trying to do something like this. So for the rest of the talk, for the large bulk of the talk, I wanted just to describe in a brief overview some of the results that come out of these simulations. And again, this is mainly to try and persuade you that we can learn things from these simulations, even though they have inherent limitations in some of the models that we adopt. And so I'll be going back and forth between the illustrious and the illustrious TNG simulations, and to show you some results from each of these. And so one thing that we obtained from the original simulation was that the simulation produces a population of galaxies that, at least superficially, looks a lot like what we see in nature. And so this is a sample of galaxies from illustrious at redshift 0, and you can see that the galaxies neatly fall into these different categories. Most of them look like rotationally supported disks that are actively star forming. Some of them even have bars in them, like these ones down here. And then a minority of the galaxies look like spheroidal types, like these elliptical-like galaxies. And an even smaller fraction look very irregular in their appearance and are usually associated with interactions and mergers. And so if you count up the fraction of galaxies in each of these classes, it's about what we see in the real universe. And so that doesn't prove that the simulation is correct, of course. There are a lot of uncertainties present, but it's reassuring that starting from cosmologically motivated initial conditions and using simple, reasonably well-motivated models, we can arrive at a population of luminous galaxies that looks like what we see in nature. This is another comparison that was done by Greg Snyder, who used to be a student here. What he did was he took the simulation and produced mock Hubble ultra-deep fields. And so this is the actual one on the left. This is what comes from the simulation through his analysis. And at least at first glance, they look pretty similar in terms of the number of objects and the colors that they have. If you start to stare at it very closely, you'll start to see differences between them. So obviously, they're not identical. But again, it's reassuring that the simulation produces things that look realistic in terms of describing ordinary galaxies. Now, it turns out that The simulation also produces unusual types of galaxies. And so I wanted to spend a bit of time discussing a number of these because I think they're interesting and teach us things about these objects that are surprising in some respects and in some cases very unexpected. And so the first class of galaxies I wanted to mention are things called shell galaxies. And so this is work that was done by Roxana Popp here. And so this is an example of an observed shell galaxy, NGC 3923. It's a large elliptical galaxy, and you can see it's surrounded by this set of shells that interleave in radius around this object. And so we would like to understand, why did this object have the appearance that it does? And so this is something that was first studied observationally by scientists in Australia, Malin and Carter, and analyzed by Peter Quinn in his PhD thesis there in the 1980s, and subsequently studied by others, including myself. And so the idea is that an object like this at one point looked like just a featureless elliptical galaxy, but then it merged with another object. And what we're seeing here is the debris of the disrupted secondary object that fell into the larger system, producing these shell-like features around the central galaxy. Now, it turns out in our cosmological simulations, we see objects that look very similar to this. This is just a handful of them drawn from the original Illustrious simulation. And in particular, if you look at, say, this one here and start to count the number of these arcs and their distribution about the center of the galaxy, it's very similar in appearance overall to NGC 3923. And so given the fact that they look similar, we can use the simulation to understand how these originated in time from the simulation, and possibly use that to understand why this galaxy looks the way it does. And in the original work done by Peter Quinn and myself and others, the proposal was that what happened was that there was a large elliptical galaxy that cannibalized a much less massive companion, and the debris from that produced these arc-like features. Now, what Roxana found in her analysis is a slightly different story, that the shell galaxies are produced by mergers, but not the sort that people had imagined originally. And so what she looked at was a population of very massive galaxies, looked at their most recent merger, and in particular identified the galaxies that ended up having shells around them, like these ones down here. And so this diagram just shows the mass ratio of the most recent merger that the galaxy experienced, the radial velocity of that merger, and then this just indicates when the event actually happened. And so in this diagram, the ones that end up with shells at redshift 0 are the ones that are filled in, these solid circles here. And so you can see that they're mostly confined to this diagram of this corner of the diagram. And so the mass ratio of the event that produced the shells is typically between about 0.1 and 1. And so what this means is that unlike previous expectations, at least cosmologically, the sort of mergers that produce these features are more like major mergers, as opposed to ones where the mass ratio is very high. And that doesn't mean that a low-mass object falling into a larger system in principle couldn't produce shells. It just means that cosmologically, given the orbital evolution of such an interaction, those events are disfavored. And in fact, it's major mergers that are more important for producing the actual shell galaxies we see in nature. And so this can be tested by using things like observations of the metallicities of the shells in comparison to the central galaxy because of the mass-metallicity relation for galaxies. Okay, here's another example that's the basis for work that's being done by Kelly Blumenthal, who's here. And so she's been studying interacting and merging galaxies. And so here are just a few examples in reality. So this is what's known as the mice. This one here is the antennae, although it doesn't really show up very well, but it has very long tidal features streaming out of the bodies of the two galaxies. And it turns out in the simulations that similar kinds of objects are present at redshift 0. And so, for example, this one here, again, it doesn't show up very well because it's so light in here, but this one has fairly large tidal tails extending out like that from the bodies of the galaxies, much like the appearance of this one. And also, if you were to view this galaxy here from a slightly different orientation, it would also look much like that. And so what Kelly is using these simulations for is to understand the types of orbits that produce features like this, and the distribution of dark matter around the galaxies that will result in these extended tidal tails. And what she wants to do is to use those as a way of setting up idealized simulations where we can study this sort of event in much higher resolution than is possible in a cosmological simulation. Another interesting type of galaxy that appears naturally in the simulations are what are known as jellyfish galaxies. And so this is work being done by Annalisa Pilipich and one of her postdocs, Yoon. And so here's an observed example of a jellyfish galaxy. And so you can see there's a disk galaxy here with this trail of gas extending behind it. So what we think is happening is that this thing is moving through the background medium of a much more massive system, and ram pressure stripping is producing this extended tail of gas behind the galaxy. And it turns out that objects like this are present in the simulation with about the observed frequency of real jellyfish galaxies. And this is just one example here. This is the same object, but with the background gas subtracted, just showing the distribution of gas in this disk as it plows through the surrounding medium, leaving this trail of gas behind it. And so we can use simulations like this to understand the frequency of occurrence of this sort of event, depending on things like redshift and the host halo mass, and relate that to actual systems. And here's another beautiful image that Annalisa produced. So this is actually showing, well, this is one particular cluster that contains a number of these jellyfish-like galaxies in it. And what's shown in this panel here is a projected Mach number of the gas around the galaxy. And so you can see in each case that there are these well-defined bow shocks in front of the galaxy as it moves in that direction, with the gas tails extending behind in the opposite direction. And so we can use simulations like this to make predictions for, say, the observability of these bow shocks. And I think they could be quite difficult in principle to abuse, but if it were possible, one could use that information to say something about, for example, the density of the surrounding medium that is ram pressure stripping these galaxies. Okay, here's one example, which is one of my favorites. That's particularly bizarre and was quite surprising to me that we could actually see something like this coming out of the simulations. And so this relates to an object called Malin 1, and this is work that was being done by Qirong Zhu while he was a visiting postdoc here. And so Qirong has been studying low surface brightness galaxies in these simulations, and it turns out that there's a population of low surface brightness galaxies, and you can use the simulations to understand why, at a given mass, the low surface brightness galaxies differ from the higher surface brightness ones. And so, in general, what the main controlling reason seems to be the spin of the dark matter halo. But in the course of this study, I identified one object which has really bizarre properties that relates to this object called Malin 1. And so these are some observations of Malin 1 from a paper by Boisier and collaborators from 3 years ago. And so these are images going down that are done in different wave bands, so U, G, I, and Z. And if you look at the shorter wavelengths, like say this one here, you can see that there's an extended disk that has spiral patterns present in it. If you go to these longer wavelengths, this outer disk is mostly invisible, and instead you just see this compact object at the center. Now, well, it's obvious by eye that this is a low surface brightness galaxy, but the thing that's really bizarre is we fit light profiles to it. The scale length of this extended disk here is something like 40 or 45 kiloparsecs, okay, depending upon the wave band that you look at it in. And you can compare that to the exponential scale length for ordinary galaxies like ours, which is closer to 4 kiloparsecs or so. So this one here in linear dimension is 10 times larger than a galaxy like ours. So it's truly bizarre in its structure. And furthermore, this is a little bit more difficult to do because you can see it's mostly face on. But if you make the best attempt that you can at fitting a rotation curve to it, the circular velocity turns out to be of order 400 kilometers per second. And this is just an indication of what the estimated circular velocity is in different components, depending upon how you actually do the deep projections. Okay, some other properties about Malin 1 are that if you look at this extended disk, it's very clumpy. And furthermore, the star formation happening in this disk is also fairly clumpy. So the extended disk is present in both the stars and the gas. And there have been some attempts to try and estimate metallicities for these different knots of gas. This has turned out to be quite difficult, but typically you estimate metallicities that are less than solar. The typical value might be 0.2 or 0.3 solar. So we'd like to understand why this object has this unusual appearance. It seems to be a very unique object. Now, it turns out in our simulation, and he found this just by doing the study of low surface brightness galaxies, that there's an object that looks very much like Malin 1 in detail in its properties. And so that's shown here. This is the gas component going down. This is the stellar component. And if you look at it face on, you can see that it has this extended disk with spiral structure that's fairly clumpy. And so if you fit an exponential profile to this, it turns out that the exponential scale length of the disk is about 45 kiloparsecs, so very similar to Malin 1. And furthermore, the star formation that's happening is doing so in clumpy regions, not smooth like, say, a typical face-on disk galaxy of higher surface density. In addition, the circular velocity is similar to what we see in Malin 1. So what's shown here in the background is the actual azimuthal velocity of the gas in this disk. This solid curve is what the rotation speed of the gas or the material would be at a given radius. And so the fact that they agree means that the gas is rotationally supported. And furthermore, you can see that the peak circular speed is a little over 400 kilometers per second. Again, very similar to Malin 1. And so we can use the simulation, at least if we think that this is a representation of what actually happened, to understand how an object like Malin 1 might have originated. And so this is just a snapshot at different times showing the galaxy's appearance. And so at high redshifts, above redshift of 0.4 or so, it looked like an ordinary high surface brightness galaxy with a typical exponential scale length. But by redshift 0, it had built up this much more extended outer disk component, and we can use the simulation to understand how this actually came about. And it turns out that what happened in this case is that the central galaxy had a merger with another system, but it turned out that this system consisted of a binary pair of galaxies. And so the central galaxy is in the middle here. These are the trajectories of the two infalling galaxies in this binary companion, and the numbers indicate the redshift. And it turned out that in this companion, one of the galaxies was very massive and gas poor, and the other galaxy was relatively less massive and gas rich. And during the course of their in-spiral, the interaction between these two stripped off a lot of gas from the lower mass gas-rich companion that settled into a disk surrounding the central galaxy. And because that gas still carried the angular momentum of the orbit, the distribution of that gas was very extended relative to the central galaxy. And so that gas naturally cooled and settled into a disk. Furthermore, it mixed with the hot gas in the halo of the central galaxy, accelerating the cooling of that gas. And that led to the buildup of this extended gas disk by redshift 0 through this binary interaction. And so this naturally leads to this sort of possibility for how Malin 1 came about through some sort of three-body interaction like this. And of course, this would be a very unusual event, which is perhaps why we see only one example of this nearby our galaxy. And so the simulation makes other predictions that can be used to test this sort of scenario. For example, we can measure the metallicities of both the gas phase and the stars. And so there's an IFU project that I'm involved with Lisa Cooley that's going to try to obtain very high detailed information about Malin 1 to test it against the predictions that come out of this sort of simulation. Now, you might think that this is just a very unusual case that may have nothing to do with more general situations, but here's an example of something that this might actually happen to, which is our galaxy. And so in the context of the model for the evolution of the Magellanic Clouds that Gertina Bessela formulated when she was a student here, the Magellanic Stream is a consequence of the interaction between the two clouds before they came into our galaxy. And so the speculation is that if this gas retains its angular momentum, settles into our gas in a much more extended distribution than the Milky Way itself, and possibly mixes with the hot gas in the halo of our galaxy and accelerates the cooling of that gas, that maybe our galaxy could evolve into something that looks like Malin 1 eventually. Okay, a few other examples of things that we might learn from these simulations. So I didn't say much about this, but it turns out that at least in the TNG simulations, that the color distribution of the galaxies is very similar to what we see in reality in, say, the Sloan survey. And there was this nice paper by Dylan Nelson from last year that you can look at, where he compares it in detail to the observations. And so in this plot is shown the distribution of G minus R color versus galaxy stellar mass. The underlying shaded region here is a distribution of galaxies by color at redshift 0. These are the blue galaxies and these are the red ones. The dotted lines, which are a bit harder to see, are ones at higher redshifts that are progressively shifted downwards because everything was bluer at earlier times. And then superposed on top of this are evolutionary tracks followed by just a handful of the galaxies to show you the sort of diversity that we see in galaxy evolution. And so, for example, this one here is always a blue galaxy and oscillating through this so-called main sequence. And so Sandro Tekela is measuring these oscillations to try to compare those to observational data and to see if we can understand what's responsible for this sort of oscillatory behavior. A galaxy like this started off blue, it became quenched and became part of the red population and then didn't grow much in mass. But there are other examples that were initially blue and became red and evolved significantly through the action of gas-pore mergers. And finally, there are more unusual examples, like this one here that was blue, became red, then became blue, then became red, and then became blue again through the action of gas-rich mergers and some residual gas accretion. And so we can use simulations like this to estimate the fraction of galaxies that display this sort of unusual behavior and compare the statistics of that to what we see in the real universe. Another thing that we can do with the simulations is we can measure the transit time between this blue population and the red population as galaxies become quenched. And that resulted in something interesting that we're trying to understand now. So this is just the distribution of timescales to transit through the so-called green valley. So if a galaxy had its star formation instantaneously turned off, it would take about a gigayear or so for the stellar population to age enough that the galaxy would be classified.